All right, so let me quickly, because it was a little rushed at the end of the last lecture. Um, Let me just sort of review what we had said. All right, so we were talking about I was kind of racing towards a formulation of a complete future null infinity and then the corresponding cosmic censorship conjecture, which is the statement that you generically have a complete future null infinity. And so there were two sort of steps to this. We started with, we said, so everything is in terms of the initial value problem. So we always start with initial data. Um, so I said, suppose you have sigma hk is an asymptotically flat initial data set. All right, and remember that means that this is a three manifold, and then if you take out a compact set, so you can find a compact set that if you take it out, then it looks like Euclidean space minus a compact set, and in those coordinates as sort of r goes to infinity, your metric converges. Looks like the Euclidean metric in this symmetric 0, 2 tensor goes to 0. And again, you of course, if you want to actually do any real analysis of it, you have to make that quantitative in some way. I gave an example of something called strongly asymptotically flat data, some decay rates. Anyway, there are different ones you can work with. It's not important for this discussion. Well, it's important if you want to prove things, but not important at the treatment that I'm going to give right now of this discussion. All right, so I said we have this. Then what you can do is I'll sort of schematically draw this sigma here. And then what we could do is, okay, and then I'm going to, you know, sort of imagine here's my compact set W that I take out. So I have no idea what's going on there, but I know that outside, so here's sigma take out W. I was gonna close that door. That door is closed. So nothing we can do about the noise. If we take out W, then in this region here, the metric is close to flat space, and it's a theorem that you can equip this with the double null foliation. You can equip this region. You can draw this little region here. And so here you have a double null foliation. But we don't really need that much information about it. All that I wanted to know about, you could say a lot of stuff here, but the main thing I want to know is that you can pick a hypersurface. So here I'm drawing sort of the Penrose diagram of the development of just this part of the data, right? So this is the this is the every point here, is uniquely determined by this part. I can't write anything here because then I would need to involve this data, right? Okay. So then all that I can do is I can find here I can find a hypersurface, which we could call H. It doesn't really, or C, whatever, doesn't matter. I think I called it H naught before for some reason. This is a null hypersurface. Terminating on which extends out to null infinity. And when you go along this null hypersurface, the geometry becomes closer and closer to the geometry um, of flat space. And that's what I sort of needed I just wanted the existence of that in order to of such a hypersurface what I need to give my definition of the particular definition I gave of a complete future null infinity, which was then, so once we had this, so then you choose some L bar, which is transversal to H naught and null, say somewhere. All right, so you just pick this vector like that somewhere, L bar. Then we parallel transport it, and we can parallel transport L bar to all of H naught, so that defines it everywhere. So when you choose, remember, null vectors, there's not, there's no way to pick a canonical normal vector to this null hypersurface because it's normal, it has to be a null vector, and there's no way to pick that size. So, so there's kind of no natural, and then this L bar is a normal vector, which um is a null vector, which is pointing in the other direction than the normal to the hypersurface, but there's no natural way to normalize it, right? So, but I sort of deal with that by I just pick anything I want, then whatever that is, I parallel transport it. And because the anticipate, I mean, I'm going to say it again, but remembering before that the things we're interested in are whether some affine distance is finite or infinite, the just scaling this by 2 or 1/2 wouldn't change the answer. So it's just you pick whatever and then parallel transport it. That's fine. All right, so we transport it there. All right, so you have at every point every point on the hypersurface you have this um this L bar, and then all right, and then what we want is that you can right, then for each, then if P is in H naught. I forgot what I called it, but it doesn't matter what it is. You can say this is defined to be the maximal affine length of the geodesic gamma with gamma of 0 equals P and gamma dot of 0 equals L bar. All right, so that's you're going to shoot in an ingoing geodesic into your spacetime. Now, you don't expect that in general might not live forever. Certainly doesn't, for example, on the Schwarzschild spacetime. All right, but you can still look at that number, and then the sort of we say we have a complete future null infinity if I'll write it like this: the limit as p goes to infinity of a of p equals infinity, where this limit as p goes to infinity means as you pick points, so sort of in the topology of the diagram. So as p gets closer to future null infinity, so as you go further out on the null hypersurface, these lengths that these ingoing null geodesics exist for should go to infinity. Yeah.
But the geodesics may leave this development set of sigma without.
Yeah, we're not. That's fine. Yeah, this is maximal affine length in the maximal globally hyperbolic development of sigma.
Okay.
Yes. Yeah, I just needed this sigma. This is just some technical thing. I could have started just by assuming that you pick some H naught in your spacetime. I'm just saying that, really just from the data being asymptotically flat, you can always, if you go far enough out, you can find some null hyper. It is actually true that you can always find such null hypersurfaces.
Thank you.
All right. Okay, it may be okay again. So this is definition. It's sort of one of the weakest ones you could imagine, but that this will sort of suffice, and it has the interpretation that if you are a faraway observer of some isolated event, that sort of in the limit as you are very, very far away, as you're infinitely far away, you will exist forever and can do observations forever, even if singularities form in spacetime. Yes. All right. And even though it doesn't explicitly sort of mention this, it's intimately related to the idea that singularities, if they occur, if there's a singularity, then it might be hidden inside a black hole region, like in the Schwarzschild picture that I drew, even though the word black hole doesn't, appear here. But okay, so there are questions about that? I said that all sort of fast the end last time. Any Zoom questions? I'll try to. I know the last time there were some comments in the chat that I wasn't checking, so I'll try to check. Okay, so that's fine. And then the weak cosmic censorship conjecture is the statement that or that generic initial data sets have, I mean, this is one, I'm sort of stating it a little informally. I'll say some more things in a second. Have a complete future null infinity. All right, so generically, you know, you can think generically we can do astrophysics. There's not a problem, which is good if you want to do astrophysics. Okay, so let me make some quick remarks now. Okay, so some things that are important here. Maybe first comment. So first of all, so let me make some remarks. So first of all, I've stated just saying initial data. There's some, you want the initial data and at least the focus in this course and the interpretation of this conjecture. It's important for that the initial data, be sufficiently nice. And one aspect of that is you should, we will, we are interested in, sigma hk, where sigma h is complete as a Riemannian manifold. Right, because otherwise, I mean, well, intuitively, it's kind of, if your initial data is not complete, then you have some, it's like you have some part missing of your initial data, then it's kind of, well, then of course weird things might happen, in your solution. That's not really what this conjecture is trying to talk about. A nice example of this situation that is good to work out for yourself. So e.g., if you have negative mass force field. So if m is negative, right, then you can look at this metric. This is the same as you can look at the Schwarzschild metric. Right. And so now, so before, initially m was positive and this metric had a problem, this form of the metric had a problem when r was equal to 2m, right? So now, because if m is negative, there's no analog of that point. There's still r equals 0. But you can check, so this is at first defined, right? You can just do, you can't, there's still an issue at r equals 0, right? But this form of the metric now makes sense here, and what you can check is the Penrose diagram. Again, this is spherically symmetric spacetime, so it's especially no big deal making sense of the Penrose diagram. And you can, yeah, it's a sort of exercise. So this is actually what the Penrose diagram looks like. So this is so it kind of looks like Minkowski space, actually. So there's r equals 0. And you still have this part, which you can call future null infinity, past null infinity by analogies with Minkowski space. But so this is, of course, the big difference with Minkowski space is this thing is singular. Right. And what you can see is that, for example, the t equals 0 hypersurface here. I mean, just in the diagram, you see that if you try to draw some a hypersurface, which you would want to be in the Penrose diagram, looks like it might be a Cauchy hypersurface. I mean, it's going to hit, for example, this a singularity here. So it just doesn't, this is in some sense an example of a naked singularity in that, well, I mean, the different ways to, if you looked at the development of this, maximal development of from this hypersurface, it actually would look like this. That would be the region you could get. All right. This point is singular. And you can check that this, you know, basically, if you start here, these distances are all going to be finite. All right, so you can exercise. So exercise. This is a naked singularity, or by this, let me say the maximally globally hyperbolic development of t equals 0 in this. Right? All right, but we kind of we don't want to count this for what we're interested in because it's kind of cheating because the initial hypersurface already has a singularity in it, right? So it's kind of
Yeah, but wouldn't a Schwarzschild, like the Penrose diagram or the regular Schwarzschild metric that has like R equals 0 at the top, so that also
but your initial hypersurf, you can your initial data, which leads to it, doesn't go anywhere near that. Yeah, that's fine. The initial data for so I didn't have a full discussion of Schwarzschild here, but for those that are familiar with it, there Cauchy hyper for the maximally extended Schwarzschild, you can find smooth Cauchy hypersurface, which is it'll be diffeomorphic to R cross S2, but it's just smooth, has two ends, but each end is asymptotically flat. So there's nothing objectionable about the positive match Schwarzschild data. But here, this is objection. All right, so that's first comment one. We want to look at complete things. It's three. All right, somehow I'm going slowly. Okay, and then another comment that I wanted to make is that, this is all in principle. In principle, this is all sensitive to the functional framework that you use to study the problem. Sensitive to, and I'll say what this means. This looks a little vague. To a functional framework used to understand the Cauchy problem. All right. So what do I mean? So far, I talked about the existence of maximal globally hyperbolic development. I just phrased everything. Well, I didn't talk at all about proofs really or anything. And I said, let's consider you have smooth data, blah, blah, blah. All right. Well, in reality, and very soon we're going to consider things that are not smooth, even less regular than C2. Yeah, so maybe I should say a few words about it. So all over in general in PDE, one of the things you learned is that, there are lots of different, function spaces that are reasonable to work in. And, and it's not kind of just insisting on working only with smooth solutions might, can be sometimes, maybe many times in PDE is perfectly fine, but sometimes it's a little sort of, in reality, you miss important phenomena. So famous example, like shock development, which are real physical things. And if you insist on studying smooth solutions, you can't study them because they're just not smooth, but they're reasonable. Okay, so all that being said, so what do I mean by this? So first of all, what kind of data you want the class of data you consider should be such that you have well-posenness. All right. And that I mean in the sense of what you learn in a PD class. So well-posenness means you pick whatever your space of data is. It doesn't have to be smooth, but you should always have the existence of a solution in a certain function space. Within that space, the solution should be uniquely determined by the data, and you should have continuous dependence on initial data. At the very least, you might want some other things depending on what you're trying to model physically, but at the very least, you should have that. And then, okay, so first of all, so depending on what framework you work in, certain initial data may or may not be reasonable, and that can affect whether or not something, is like causes an incomplete future null infinity or not, right? So you should fix this in principle. You might hope that the answer doesn't depend on it, but in principle it could. All right, and related to this, so this affects the data, but then also the maximality of the maximal globally hyperbolic development, could depend on the data too. Could depend on functional framework too. Now, this might seem a bit surprising if it's the first time that you are thinking about this. So what do I mean by this? So remember the definition, again, if this is your first time thinking about these objects, just, first, remember, just think about ODEs, right? You have some data, then there's always this canonical object. This is maximal. There's the biggest solution that you can find, and then how do you know it's the biggest you can find? Either it exists forever, or if it doesn't exist at some point, something goes bad. There's a singularity, right? It's the same thing here, but the point is that, so you find the biggest one that you can find, it means something is going sort of wrong. Either it's global or something's going wrong at the end. But the question is, what could go wrong? It could be if you're insisting on studying smooth solutions, and if the solution all of a sudden is only C500, then you have to stop. But maybe you say C500. I mean, like that's surely 500 derivatives don't matter for anything physical, right? I mean, surely 2 is enough. So then maybe you can keep going. So, but that will change what is the maximal development. So this is a subtlety, right? So these are, of course, intimately related issues, but are distinct in principle. All right. So, okay, that's the 2 main remarks I wanted to make about that. Any questions? Okay. Let's see. Next thing I want to do, so I want to define now the what sort of, so the description of this course has the word naked singularity in it. So I want to, oh, and I even used it there and I didn't define it. So, you're supposed to complain when I do that. But now let me define what naked singularity is so that you can do that exercise. But maybe it was sort of clear. All right, so definition. All right, so if a space-time mg is the maximal globally hyperbolic development of sort of, I'll put in quotes, of reasonable data, a reasonable initial data set. All right, we're reasonable in quotes. It's reasonable in quotes because it's sort of, you make an, because of this remark, you make an argument about what's the right state, what space you want to work in. Different people could have different ideas of what they want to work with. So whatever you decide upon, if it's a maximally globally hyperbolic development of a reasonable initial data set and has a reasonable asymptotically flat initial data set of and has an incomplete future null infinity and has an incomplete future null infinity, then mg is called a naked singularity. All right. And again, this sort of colorful terminology of naked is related to the idea of the black holes and you always think about the Schwarzschild example. There's a singularity, but it's hidden by the black hole to observers which are far away. And so if that doesn't happen and observers who are very far away can see it, it's sort of naked, right? And yeah, that's what it is. Okay, and then so we sort of had this exercise about one sort of picture of a naked singularity. Here's sort of a naked singularity kind of arising from not reasonable data, as I said. So what's sort of a typical typical Penrose diagram is something of the following form. So you should think you have some reasonable initial data. All right, let's suppose maybe you have either it's a spherically symmetric space-time or there's some sort of axis of symmetry, so you might have some thing like here, like a Minkowski space, and then all of a sudden there could be a singularity here. Oh, actually, I'm gonna run out of space. Yeah, so so here is our singularity lying on, say, some time-like curve. This was our initial data set. Let's go out like here. All right, let's yeah. Then out of here we had sort of our future null infinity. Here's the singularity. Here's the future like cone of the singularity. So once there's a singularity in your space-time, again, I'm using the word singularity without telling you what kind of singularity. So singularity, depending on whatever, that means that you have to leave whatever functional framework you decided to work in. Once there's a singularity, then you can't solve, in something that would causally depend. So you get stuck here. And all right, so now you can draw this outgoing hypersurface H naught. And then you have these ingoing geodesics gamma, right? Blah blah blah. And these all have uniformly bounded affine length. All right. So this is sort of a typical pic. I mean, this is not the only kind of thing that can happen, but this is a typical thing that you might think that happen. You have a singularity which forms, then you have to stop solving your space-time at the future light cone of that singularity. All right. Doesn't mean this stuff could be singular or not. It doesn't really matter, but it's even sort of weirder if it's not singular. So it's just kind of like you have to stop. And then you're way out here trying to sort of do your astrophysics really far. You're going along, and then at some point, like your space-time just can't even, I don't know, you can't solve, there's no space-time to exist. Right. So this is kind of the typical thing to have in mind for what a naked singularity sort of looks like. Does that make sense? Yeah.
I guess I can have a semantic question. Like, why do we call the whole space-time a naked singularity and not just like it has a naked singularity?
People probably would use both. I mean, this is not.
Okay.
Though, yeah. So colloquially, probably that and more other ways of rephrasing it are used. It's usually not that confusing. One sort of there is this as a quick side note. There's this annoying thing in relativity, right? That when spacetimes quote unquote have singularities, they actually sort of don't, because the singularity is not a point in spacetime. It's like it's like an inability. I've sort of I haven't really. You see, these things are all defined in terms of MGHD. So you have the thing you can talk about is you solve as far as you can solve, and then you can have incompleteness. I mean, that's the easiest way to. But I still haven't given an actual definition of what would it mean to be a singular point or something. You can define those things. It would take us. It's not that important right now to do so, but note that I have it because it's kind of, as opposed to a PDE on a fixed background where it's clear what it means that a nonlinear wave equation solved on Minkowski space, you say, well, it blows up at this point. If when you approach that point, the solution blows up. But here there's no point because it doesn't exist, right? Okay. So that's so when you say it has a naked singularity, yeah, there's lots of abusive language there, even though in reality, no one is confused by that. But you should just note that it's a lot of abusive language. Other questions? Yeah.
I want to check whether space-time is known future infinity complete. We'll have to check for all the H naught, right? Or we can just check for some H.
You could check for, it would suffice to check for sort of one coming from that. So you work outside this big, again, there are different definitions that exist in the literature. You shouldn't think that almost none of this is canonical, really. There are different definitions you can give that capture the spirit. The original definitions were given often in terms of explicit conformal compactifications, which is somehow the strongest thing. But then there are all these regularity issues that I briefly hinted at that occur there. So, it's simpler to just ignore all of that and give these kind of weaker definitions. But in reality, you might want a lot more. I mean, this is kind of a weak statement, just saying these things exist forever. But yeah, you should think that it would be enough if, like, in the domain, so you're outside this compact set, then there's some domain covered by the Kleiner-Mendicolo result where you have a nice double null foliation. It would be suffice to check for those hypersurfaces. And if, of course, in that domain, it suffices to actually check one of them, and then it will be true for all of them. Yeah. But I say that, but of course it's a little, I mean, it's a little weird that it kind of, your naked singularity depends on your choice. Is that true? I don't, that's an interesting thing to think about, but yeah, for now we fix some kind of geometry at infinity that it's relative to. Other questions? All right, so then, okay, so let's keep going. All right, so that sort of closes this kind of first part of the course where I did this quick review / introduction to various notions of Lorentzian geometry, and my goal was to get basically as fast as possible to these statements. All right, so then the next part of the course, or really the rest of the course, is about trying to construct some examples of naked singularities, okay, in different settings. And we're going to sort of build up to that. So the first, so what I'm going to do next is I want to discuss some sort of just a small part of this work that Christodoulou did in the 90s concerning the spherically symmetric Einstein scalar field system. So we're going to discuss some solutions. So discuss some interesting solutions to the, and I'll tell you what the system is in a second, spherically symmetric Einstein, well, let's say Einstein real scalar field system. All right. But first, I want to say why this might look a little weird. What's the scalar field doing? Why am I throwing that in? Well, that has to do with something that's sort of quite annoying about the Einstein vacuum equations. 3+1 dimensions, which is the following. So in lots of PDE, one of the nice things when you're trying to construct singularities is that you're sort of free to, to impose symmetry, right? If you're trying to find an example. I mean, if you're trying to prove global existence for some nonlinear wave equation in 3 dimensions, well, you have to study all the things. If you're trying to show that something blows up, we just have to find, you're allowed to find one solution, kind of, right? And so in particular, you could always study spherically symmetric ones. And that's sort of in problems which naturally admit a notion of spherical symmetry, which the Einstein equations certainly do. Then you think, okay, if you're trying to find, the first thing you do is always look for spherically symmetric examples because that's the easiest thing to work with. But there's this really annoying thing about the Einstein equations, which is that when you oppose spherical symmetry on 3+1 dimensional spacetime, there are basically no dynamics. There's rigidity. So this is called Birkhoff's theorem. I forget the year. That's quite old, actually. Of course, well, doesn't predate the theory, but otherwise quite old. Birkhoff's theorem. So the only, well, so if mg 3+1 dimensional Lorentzian manifold solves So let's say Ricci of G equals 0. And it is spherically symmetric. All right, let me not formally state what spherical asymmetric means right now. I'll say something in a second. And it's spherically symmetric, then locally mg is isometric to a subset of Schwarzschild for some mass parameter m. Right. So remember that on Schwarzschild, I don't know if I explicitly said this, but in the Schwarzschild metric, if you set m to be 0, then you just recover Minkowski space. Right? So that's okay. So this is pretty annoying because it says that if you want to study, I mean, you can't. In particular, note that all the Schwarzschild metrics, remember, don't depend on they have this. They only depended on the r coordinate, so they have like a killing field, an extra symmetry, which of course sort of at least for a large enough r corresponds to what normal notion of time translation. So they're what's called stationary spacetime. So in particular, all these spherically symmetric ones have to be stationary. And well, so you sort of can't you can't study dynamics. So that's pretty annoying. Okay, so well, first of all, so is that clear? Yeah. All right, so then you say, all right, I mean, so you have two options. You can just try to study non-spherically symmetric Einstein equations. Okay, those are, well, eventually we will do that. But okay, those are pretty just at an algebraic level, it's just complicated. And so it's still important, like in all of mathematics, important to have simpler problems that you use to build up to more complicated ones. Right. And there's sort of this model that has, in many situations, I mean, famously in this series of works of Christodoulou, has proven to be a model that captures a lot of, well, some conjecturally captures, some we provably captures lots of interesting phenomena of the Einstein vacuum equations, but is a spherically symmetric model. And this is to couple with the scalar field. So, right, so we can do Einstein real scalar field. So what does that mean? That just means that we will do the following. Right, so in addition, so this system, okay, so we still have our 3+1 dimensional Lorentzian manifold. Right, and then we add one extra degree of freedom. So we're really we don't want to add a lot into the problem, just the minimum amount to break this theorem so that we can study something. So we're just going to add a single function from m into the real numbers. Right, we're not even allowing it to be complex value, but really just one degree of freedom. All right, and then so there's a canonical way to couple the Einstein equations with a matter field. So what do? You take the Ricci tensor, right? And this is supposed to equal the energy momentum tensor. I forgot if I wrote this at the beginning of the course, but okay. This is called the Einstein tensor. Okay, so this is kind of the geometry side, and then this is the matter side. And so I need to tell you what the what TAB is for a scalar field. So for scalar field, TAB is equal to the alpha of phi, e beta phi minus 1/2 g alpha beta, g gamma delta. All right, so this is the stress energy tensor of a scalar field on space-time. And then, all right, so it turns out that for any metric, this tensor, if you form it, is always divergence free, right? And so if you have a solution to this, then you would need, that the divergence of that equals 0. And of course, the divergence of this, nice little calculation, is exactly equal to box G of the scalar field times d beta phi. Right. And so that being 0 will be true because we also will require that the scalar field solves a wave equation. So we require that right. So that's the Einstein scalar field system. I haven't imposed spherical symmetry yet. This is just so I have the Einstein equations. Then so this part will drive the metric, sort of you think forced by the phi, and then at the same time phi will solve a wave equation, of course, which itself depends on the metric. Yeah.
So is phi here supposed to represent like a matter field or being?
Yeah, it's an extra thing. Yeah, it's matter. So I mean, though not some like familiar matter from like I mean, it's more of a it's like the simplest possible matter you consider, just one real degree of freedom, right? Yeah, you could do it's just the simplest thing. And so and the idea is that, you know, I mean, in many situations, the metric sort of behaves like a wave, right? You know, I mean, okay, in harmonic coordinates, it literally is a quasi-linear wave equation. If you linearize around Minkowski space, it literally solves wave equations. There are a lot of wave equations floating around. And so we're going to impose spherical symmetry, which we know will destroy the ability of it to have dynamics. Then we're going to try to restore it in a simple way. So the idea is we want to that if we restore the wave equation, maybe it'll kind of still act like, you know, the Einstein equations, right? I mean, we could put a lot of things here, then study them in spherical symmetry. But if we put something weird, why maybe it's not going to be useful for why would it be useful for uh you know, for understanding the Einstein vacuum equations? Okay. Other questions? Check the Zoom. No, everybody is good. All right. So now let's impose spherical symmetry. Let's see what we get. All right, so now on this system, we're going to impose spherical symmetry. So again, what does that mean now? So that means, so we assume that the isometry group of the sphere acts on the space-time. So we have an action of SO3 on our space-time. All right, so away from the, so SO3 is compact, of course, and so away from the orbits, we want, I mean, away from the fixed points. So away from the fixed points, you know, the orbits we want will be space-like. Orbits we require to be space-like sub manifolds, you know, Defio 2s2, right? And we do want to allow fixed points because, of course, we, you know, we always have Minkowski space in mind. That should be an example. And Minkowski space has r equals 0, right? Which is a fixed point of the action. And we want the set of fixed points should be a time-like curve gamma. All right. Maybe we'll say some more things later. Again, maybe it's worth, I sort of repeatedly give these kind of caveats. Again, you can easily give a whole course about, you know, well, just studying what Christodoulou did about this system. So that would take a lot of time. I'm just going to focus on the things relevant to naked singularity. So I'm going to leave out a lot of stuff. Okay. All right. So then, so we have that. So now let's let Q be quotient of M by the action. All right, so then Q will be a Lorentzian manifold with boundary. So, so it's just like, think just like the Minkowski space. So it has about, this is related to the fixed point. So Q will be a 1 plus 1 dimensional Lorentzian manifold with boundary, where the boundary of Q is just going to be basically this set of fixed points. Right? Again, if anything seems confusing, just think about Minkowski space, right? Okay, so all right, let me just write out the system and then we'll take our break. All right, so then on this quotient manifold Q, all right, so now we're going to always work on the quotient manifold Q, but we want to remember some things from the geometry upstairs, but the things that we've quotiented out by, the information in them is all stored in the function R, which gives the radius of the corresponding sphere. So we define R from Q, well, it can be 0 to the non-negative reals. So by that R of Q is the area of the corresponding orbit. Corresponding SO3. Right, every point in the quotient is, you've collapsed an orbit of the action, you've collapsed the sphere to a point, and this just records what the value of that area is, right? Just like the R function in Minkowski space, right? Okay, so we have this R, and then we have this, and we also assume that phi, so we assume phi, descends to Q, i.e. phi is invariant under the orbits, and so it makes sense to consider phi as a function here. All right, so now we work on Q, and so we gain, so things simplified in that now we have something 1 plus 1 dimensional. We just have this one remaining function from the 3 plus 1 world, and then now phi is only defined on something 1 plus 1 dimensional. And now it's a computation. So now the Einstein equations then become the following. I guess, okay, then I should also, I guess I started with G. By abusive notation, I will also write G as a metric on the quotient, right? So then we get the following, and I'm also gonna nabla, I sort of use nabla up there to be the connection, like when I wrote the divergence of the energy momentum tensor, right? That was the connection sort of upstairs. I'm going to keep using that for the connection downstairs, right? All right, so then the Einstein equations are the following. So there's an equation, this is an equation for the Hessian of the function R. This equals, we will see these in a slightly simpler, well, we'll make these more concrete in a second. This isn't sort of stated maximally geometrically, minus R squared, times. And hopefully I didn't make any typos when I copied this down. Okay, G. All right, so this is an equation for the Hessian of R that couples back. So on the right-hand side, it's sort of, well, you see phi, see that stuff, right? Then we have the scalar field equation. Well, that you can write, so that can be written as the following, right? So you can write it sort of purely in terms of the connection on Q, but you pick up this R squared here. This is again, just like writing the wave equation of Minkowski space for a spherically symmetric function, there's this factor of R from the usual formulas. Okay, and then the final thing is that the Gauss curvature of G. So again, on this, doing that abusive notation, this thing. So this is a Q is now is two-dimensional, right? So there's just a curvature scalar associated to it. So this has to equal R to the -2, 1 minus nabla of R squared plus nabla of phi squared, right? So that doesn't look super fun, but it is still a dramatic simplification of the full Einstein equations. All right, so well, maybe I'll ask, are there any questions?
Like,
Yeah.
phi descends to Q just means that on the orbit, phi is the same, right?
Yeah, the phi is invariant under. I just mean, so if I just didn't want to introduce the notation. So if I don't know, if n is an element of SO3, then phi of a point P should equal phi of n after so that it makes sense to just drop it to the quotient. Any other questions? All right, if not, then it's a good place to take our 10-minute break. So let's reconvene at 4:13. All right, let's get going again. Okay. So we only lost one person, so that's not bad. All right. So okay, so we're studying the system. And all right, so like I said, we're interested, all right, in general, let's say we're trying to find, are there naked singularities? I mean, I should say, I made this this was a remark I forgot to make about the conjecture. I'll just say it quickly. In the formulation of weak cosmic censorship, there's this word generic, and I even underlined it. I said for generic data, you don't have a naked singularity. But I haven't, a priori, it's not clear that naked singularity should exist. And in fact, in the original versions of the formulations of those conjectures, which go back to Penrose of Nobel Prize fame, though not for making that conjecture, was the belief was that naked singularities wouldn't happen. And it's only because of various works, starting in the 90s, that it seemed they did happen, but that they were, when they occur, at least in reasonable situations, that they were unstable. So it's still the case that sort of if you wiggle the data a bit, you shouldn't see a naked singularity. So generically, they shouldn't. All right. So our goal is to try to find some naked singularities here, but okay, as we sort of maybe have noted, these aren't, it's true, this is a big simplification from the vacuum equations, but it's not exactly a simple set of equations. And it's also not very clear how should you make something singular from it. Okay, but experience with all over mathematical physics and even broader in PDEs indicates that often a good way to find singular solutions, which sometimes may or may not end up being relevant, but a good place to look is at so-called self-similar solutions. So it's so often good to look for self-similar solutions. All right, and what does that mean? All right, so, well, I'll sort of give a definition first for this scalar field system, where it's a little, because of the geometric nature of the system, it's a little more confusing than it would be for concrete PDEs. But then we're going to immediately focus, probably for most of the rest of the lecture, on the same definition, but applied just to the spherically symmetric wave equation on Minkowski space, right? Because that, basically you have to understand that before you can do something more complicated. All right, but let me first sort of give the kind of general framework here. So the first point is that there are two important symmetries, right? So what does this mean? What is this? All right. So the first thing to say is there are two fundamental, say it in sort of maybe the cleanest way to say it is there are two fundamental group actions on the space of solutions. On the space of solutions to the to our system. All right. One of them, well, the first one is sort of what seems to be the more interesting one. The second one will seem to not be very important, but will turn out to be crucial later. All right, so the first one is this so-called it's kind of the rescaling symmetry. So this is an action. So you consider the positive real numbers, make that a group with, it's a group under multiplication, and that acts, all right, on our so we have a triple. So our solution, we have the function r, right? We have the scalar field, and then we have this quotient metric, right? With the metric g. Okay, so I want to say how does this act on this? So if a is here and r b solve the system, then a times r, b, and a squared g will also solve. We're also solve. Okay. All right, and this is just yeah.
What's the system here?
These yeah. I didn't want to say spherically symmetric Einstein scalar field. Solve the system. Okay, and that, you know, you can just plug it and check. Okay. Yeah, remember this. Oh, so there was a question during the break, in case the people on Zoom didn't hear. So this, I maybe said it out loud, but this is the Gauss curvature. Okay, so Waldo, so if you have a surface, 1+1, a two-dimensional object, and you multiply the metric by a number, you know, you can know how the Gauss curvature changes, and similarly, all these things will scale. And if you plug in these particular combinations of things, you'll see that the same powers show up everywhere and it works out. All right, that's the first symmetry. So this is what's known as the this corresponds to kind of a rescaling symmetry. All right. You can think that it kind of corresponds to well, I'll say in a second. It'll be easier to say on Minkowski space to think about what this means. It's a little weirder here because we're not somehow because it's this geometric setting. But okay. So that's that. Then there's one more. All right. Yeah. Questions on Zoom? No. All right. So then let's go. All right, and I said this other one seems a bit silly at first, but turns out to be really important later. So this one, it's all of the real numbers, and let's consider that as a group under addition. All right, so this also acts on this whole. You have a triple in the following way. All right, so what do I mean? So okay, so let's take B and R and suppose this solves this, then, well, you just add the constant to the scalar field. Also solves this. All right. Like I said, that one Okay, that one's easier to check, right? That's just because the scalar field equation just involves, well, the scalar field only ever enters through its derivative. So clearly it's fine. All right, it doesn't seem like such an interesting one. This is certainly when one studies just the wave equation by itself, this is not, or even nonlinear waves, it's not often a very relevant symmetry for any considerations. Okay, but that's that. Questions? Makes sense. All right. So you have these two symmetries. So these are crucial. And now, so we say definition. All right. So we say that that this triple is self-similar. Well, okay. I'm going to use so Christodoulou is actually terminology for this is scale invariant. It's because we're going to reserve the term self-similar for a generalization of this later. A scale invariant if there exists a transformation. Well, yeah, the different way you can either phrase it in terms of a vector field or you have a one parameter family. Well, I'll say if there exists a vector field, let's call it K, such that under the corresponding flow diffeom, right? So we can, once we have the vector field, we can flow by the vector field, get a diffeomorphism. This flow map depends on auxiliary parameter of how much you've flowed. Then so of course, so if we just apply a diffeomorph, so it's the Einstein equations are geometric, right? So we can always apply a diffeomorphism to our the manifold that doesn't change, curvature is invariant under that, and then we can pull back just it's just changing coordinates, pull back these functions, and we'll still get a solution, right? It will still be a solution to something, but it might not, it might change what it looks like, right? So we say that it's scale invariant if when you do this coordinate change, the way that, so you're going to get a solution, but it's scale invariant if the new solution you get is exactly the one given by this action. All right. And again, I'm sort of doing it in a weird order, and then I'll give the example which should make this more clear in a second. This is the maximally abstract way to put it. So when I pull back by this, I get A times R. I pull back by that, I just get phi. And when I pull back the metric, I get A squared G. Right? All right. Definition, okay?
We would assume that the flow is complete or anything like that.
Well, sure, but I mean, things have to make sense to be scalar, yes. Okay, so now, like I said, so we want to study these, and we're going to actually, it turns out what's kind of interesting is we basically can write these down for the Einstein scalar field system. This is something Christodoulou did. You can actually just simply write all the solutions down, more or less explicitly, which is a little surprising. But before we get to that, and in order to interpret those solutions that we get, it's I think pretty important to first work out sort of the analogs of all these contexts in the much simpler situation. All right, so let's sort of pause that discussion. Let's examine the analog of this for just the wave equation, still in spherical symmetry, because We don't want to work too hard. The wave equation on Minkowski space. All right. So first of all, so what does rescaling mean here? So in this case, it means something much more familiar. So in this case, remember we have m is minus dt squared. It's this. We have our right. We have our r squared, so that there's the r there. And now the rescaling, this just corresponds to the way many sort of problems, especially ones that have some sort of underlying physics, where the rescaling comes from is that one way to think of it is if you change your units. Sort of the description of a solution involves might be distances or something, and those are measured in units, and that's your solution. But of course, being a solution doesn't depend on that. And so that's kind of at the heart of this sort of symmetry, this group action, this group that acts on your space of solutions. So in this case, of course, it's relativity, so we have to treat time and space on the same footing. But the analog of kind of changing your units is just the fact that you can, if you do, is just taking these coordinates and sending them to sort of AT, AR, just a simple scaling of everything. And that, of course, any coordinate change will mean that you still have a solution, but this is kind of the one this is the most naive kind of change you could do. And if you do that, then the metric minus dt squared plus this, well, what will it go to? Well, it goes to exactly a squared times. All right, so this is an example of a one. So this is right. So for any a, you can do this. So this is a one parameter family of transformations, like a one parameter set of flows, such that when you pull back the metric by that change, you get this. All right. All right. This corresponds to the vector field which generates this is the so-called scaling vector field, which you can write like this. You can also write it, well, now I'm going to be off by a factor of 2. Some constant times u du plus v dd, or suitable. All right, exercise, figure out what the constant. It might be 1. I don't remember. It's like 1, 2, 1/2, something like that. Right. So this is right, and this, so the picture, right, if you're, well, depending on how you draw it, this is just, you have your origin, and then this just points out, right? Right. Okay, and then and so now what we want to do is we want to study, so now we want to study solutions phi to the wave equation, which are invariant under this rescaling. We'll study again spherically symmetric solutions to the wave equation, which are invariant under this rescaling. Okay, which, oh wait, guess I should move to the other board. Okay, which means what? All right, which in those coordinates, so it's spherically symmetric. So our scalar field just depends on t and r, right? But saying that it's invariant under these rescaling maps means that phi is if you rescale the coordinates in the definition of phi, it doesn't change the definition. All right. Okay, so that's, a much more concrete example of what's going on. So this is a special, so we're interested in the class of solutions of wave equation which satisfy this property. Right? Yeah. Now, maybe already there's something we can make some points. So first of all, why is this, I said that when you're trying to look for things that are singular, this is often useful. Why? Well, you can sort of already see it here. So let's suppose we're going to switch to, as good relativists, we'll switch to null coordinates in a second, but I'll stick to TR just for 1 more minute. So let's consider the region where T, say, is negative, right? Just because I want to divide by T a second. So from this definition, you could take A to be minus 1 over T. Remember, I'm allowed to take A to be anything positive, right? And so what I get from this, I get that phi of TR will equal to phi of R over minus T, right? This is, again, if you've looked at self-similar things before, you often see this, right? Things are self-similar, you can write them as a ratio of the coordinates. Okay. Okay, this already you can see why the analysis of you're imposing a symmetry that effectively kills a degree of freedom, of course. So a PDE for this should become an ODE. This now depends on one variable, right? It becomes an ODE. ODEs are usually easier than PDs. So that's could be profitable. Whereas the singularity comes, so this, of course, this thing, well, where it comes from is that now you can look at, for example, if so dt of phi at TR, if we're self-similar, right? Well, what's going to look like, you're going to get, well, I guess, sorry, I kind of wrote this in a weird way, a little confusing. This is equal to phi at minus 1 or, sorry, phi at, at minus 1 minus T. And this, I'm just going to call some function H of R. Right, sorry. So then dt of this, for example, is equal to dt of that. And I mean, I'm doing something very sort of silly here, just so it's all maximally clear. And then this, of course, by the chain rule is H prime of this times, right, R over T squared, right? And so you see that when things are self-similar, at least if you take, derivatives of them, you're going to get these kind of weights. This is a common thing that can happen. You get these weights. And so this could, produce some kind of singularity as T goes to 0, right? Of course, I mean, this could also vanish, right? Well, I mean, it doesn't have to happen, but this is the most like, this is the most pedant, nose to the ground, most concrete reason that self-similarity often produces singular things. It's just because this kind of scaling, means things are equivalent to dividing by one of the variables, and then when you take derivatives, that happens. It's a little silly, but that is sort of what's going on. Okay, but okay, there are a lot of things. So I mean, yeah. It's also possible that this kind of seeming singularity is just because, it's just sort of a coordinate effect that anyway, there are many situations where this won't work, but it somehow still gives the idea. All right, so now let's try to actually figure this out. Okay, and the other thing I want to say before we actually solve, one more comment. Solve. All right, so if we restrict to solutions, with smooth initial data, then we actually won't see anything interesting. It will turn out. We won't see anything interesting. All right. So you're free to, I made this kind of big deal of their different functional frame. I mean, you're free to say, I only want to study smooth things, but then somehow you won't be able to use this to gain intuition. It won't be useful. So, we're going to sort of broaden our minds and we're going to say, okay, this is a linear wave equation. So I have a very standard for linear PD. It's not a big, we can easily make sense of solutions being distributions. It'll suffice for us to consider functions. So we will allow non-smooth solutions. Non-smooth solutions. For our purposes, it will suffice to, we will allow phi to just be continuous to just be continuous. Right. And then we have all right, and then of course you might worry, what does it mean for a continuous function to solve the wave equation? But as we learn in our analysis classes, our PDEs classes, use a weak formulation, right? Okay, so right, and so what does it mean? So right, we say, so if phi is, say, just continuous, we say it solves, the wave equation. So at this point, we're just on Minkowski space, right? The wave equation. I'll write it as box. So we'll write it like this. Right? If for every H, which is smooth, compactly supported on R4, with space and time, we have phi box of H. So, right? So this is the usual thing. So remember where this so maybe by quick show of hands, people seeing this? Okay. Yeah. All right. Then maybe I won't belabor the point. But just remember that of course, in the event that phi is more regular, this is equivalent to the usual notion because you can integrate by parts, put the box on phi, and if the integral of something against any smooth and compactly supported function is 0, and if that thing is say continuous, then it has to be 0. Right? Okay, so we'll use that. Yeah, in general, one has to be wary, especially in nonlinear PDE. Different kinds of weak solutions can be quite strange, but we will proceed carefully, nevertheless. All right, so for probably going to just have to stop right in the middle of things, but that's fine. Okay, so all right, so now we want to look at the wave equation. Okay, so the different ways just to study this. All right, I want to do it in such a way that helps to build some intuition for the some of the more complicated situations we're going to look at later. All right, so I want to also introduce some other definitions. So we've already seen, so we saw before. So first of all, let's now work in null coordinates. So before we've already defined these coordinates from before, and so we can use, all right, and we can use these u, v as a coordinate system, right? And then the rescaling, and you can just see that the rescaling works the same way. So rescaling map is still just uv goes to a uv. Okay, so now using the same reasoning that I did up there, all right, so by arguing just like I did up there, so if we so let's work in the set where u is less than 0, say, then I can write phi of uv as h of v over this for some function h. Right. In general, if I can write f of uv as, let's say I write it as some power, so I put the because I'm working where u is negative, so I'm multiplying by minus. If I write it as minus u to some power times some h, so if that's true for some real number p and function h, then I don't know, I mean, the different terminologies I might use, but I'll say that then f has scaling degree p. All right. Okay, so right, so e.g., the R Minkowski space, the R function has scaling degree 1. Right, this is also just the same. I mean, this is not really this. This is also just when you apply the rescaling map with the parameter a, what power of a sort of comes out, right? It's equivalent. Okay. So, but this is just writing it like here because this is sort of this is useful when you're trying to convert things. This is related to converting the PDs and the ODs, right, in terms of these functions. So just for example, so right, you can write so this, which you can write as 1/2 of v minus u, we can write as 1/2 of minus u of v over minus u plus 1, right? And this is a function of v over minus u, right? Okay, just making silly points. All right, useful fact. So here's just a fact. Differentiation reduces the scaling degree by, okay, just a general, so derivatives eat up 1 power. Okay, that's essentially that calculation, right? Okay, which you can generalize to the case where there's a factor outside. So, and that works either differentiating with v, u, t, r, the same, at the end of the day, the same thing will happen. That makes sense? Questions? Check Zoom. No chats there. Okay, cool. So let's go up here then. Yes. So, all right. So going back to our wave equation. All right. So for phi, our equation is minus, so the wave equation for a spherically symmetric function phi is just this, right? Okay. Well, like we saw actually, so we in the break, somebody was mentioning John Anderson's lectures in the winter school. So like we saw in John's lectures, it's very often useful in studying. There's this nice algebraic thing with the wave equation in 3+1 dimensions that you can set psi to be r phi, and you get a very it just cleanly gets rid of this annoying term. So this then you get right. So lots of computations are often easier to do with respect to this C R. This is right. It's sometimes called the radiation field. This is the object which has non-trivial limits on future null infinity or past psi, right? Because if you go on the outgoing hypersurface for large distances, the solution of the wave will fall off like 1 over r. So it's exactly if you multiply it by r that you get a non-trivial limit. Okay, so this we can write in terms of u and v, and it becomes d by du, it's d by dv, psi. Okay. Now, of course, you can solve this just using the solution to the 1+1 wave equation, but I'm going to again just to I'm going to convert this just to illustrate some points in a simple setting. I'm going to convert this to an ODE and sort of solve it that way, even though we all know that the general solution to this is a function of u plus a function of v, right? All right, let's forget that we know that. Okay, so I want to convert this into sort of an ODE. So the idea going to convert this into an ODE. All right, so there's some things geometrically to work out. So first of all, let's draw a picture here of the Minkowski space in UV. So here's the origin. So here's UV equals 0, 0, right? And then so this thing is say u equals 0. Remember, u is t minus r, so this is just t equals r is normal. All right, and then I have the past analog of that is v equals 0. And in general, right, I have, all of these lines here are the, these are the orbits of the scaling symmetry, right? So if I know, okay, so now, all right, so what I want to do is ultimately I'm going to convert this into an ODE along a given, I'm just going to use the self-similarity to convert this d by du into a d by dv. And then I'm going to consider it as an ODE along, say, u equals -1. Okay. The -1 per se could be a different constant. That's not important. So u equals 0 is here. So say u equals -1, say something here. Okay. So once I convert it, I make this into something just involving v derivatives. Then so that's an ODE in the v direction. I can solve that along u equals -1. And all I want to say from this picture, you see, as long as like the, whatchamacallit, these orbits of the scaling symmetry, as long as they hit, u equals -1, then once I know the solution on u equals -1, and if it's going to be self-similar, that will determine it along all the space-time which lies on an orbit which hits u equals -1, right? So, so once we know psi on u equals -1, you can use the rescaling to determine it, elsewhere, not everywhere, but I'll just say explicitly, determine it on, say, the whole set where u is less than 0. All right, so let's make sure we understand where that restriction comes from. So this let's say you understand it, this thing's going off to infinity. So, I know my wave my psi is invariant. If as I move along one of these curves, it has the same value, right? So as long as I'm below u equals 0, if I, eventually this thing will hit somewhere here, and then I can read off the value. But at u equals 0, of course, it doesn't, right? It doesn't work. All right, so that kind of trick is something that sort of commonly do. So you can reduce self-similarity to reduce it on certain hypersurface, and then you can use the rescaling to determine it in the region where it's determined. If you want to go further than that, you have to consider, you might have to consider, now an ODE going in that direction, say. All right, from the area where you know it, blah, blah, blah. Okay, we're gonna do that kind of stuff often. Okay, so let's go here. Any questions?
Are the dotted lines determined by zero the solution?
No, the dotted lines just refer to, I'm drawing the orbits of the rescaling action.
Okay.
So these are just orbits of TR goes to,
18.
yeah. So if you fix an initial TR and you look at all the different A's, then that just gives you this line. And we know that the solution is invariant on that line. So once you know the solution anywhere on that line, you know it. Yeah, if you know it anywhere on the line, you know it everywhere on the line. So if I know it on u equals -1, then I know it for all the lines which hit you, but not all lines hit there.
Yeah.
Right? That's all I'm saying. But nevertheless, you can sort of, when I said you imagine you could solve it here, get everything here, and then you could sort of, if we, there's a symmetry in U and B. So if I was able to convert things into an ODE this way, I could always do it the other way, and then I could go there. And again, this is like a really silly way to, if you were only interested in solving this problem, this is a really weird way to go about it. But this is just trying to introduce some idea that is in a simpler setting. Because of course, we just know the solution is a function of u, it's a function of v of the wave equation. All right, so next thing that I want to say is, so when we convert it, we can use this kind of scaling degree thing to help us. So we know that phi has, scaling degree 0, right? So now if I do r times phi, well, if you think about it for a second, that has scaling degree 1, right? Because I can write that as a function of v over minus u, and write that as u times a function of v over minus u. I multiply two functions of v over minus u, it's still a function of v over minus u, right? Okay, so that's that. And then I know that differentiation lowers it by 1. So then I know dv of psi has scaling degree 0, because differentiation always lowers it by 1. Right? So no, I don't have to do the product rule, right? We know that. Okay. So I have d by du applied to this. I want to convert it into an ODE in V. Well, I say, okay, dv of this equals h of v over u for some h, right? That's because it has scaling degree 0. Okay, so now I can check. So of course, it's clear that u derivative of h will relate to, the u derivative of this expression will relate to a v derivative of this expression, and I can easily compute that. So quickly in this business, you don't have to, you just remember the answer, but let's do it. Right, so now let's compare. Well, let's compute what this is, and then we'll compare it with dv of the same thing. So this, I just do the chain rule, right? And I get h prime of this, and then I get v over u squared, right? Okay, on the other hand, dv is h prime of this times this. And so the upshot is that this equals v over minus u times dv. Okay. So the point of this, and and sort of a straightforward generalization of that calculation is that so just by not scaling degree, right, we can convert, u derivatives into v derivatives. Or if you were a very Newtonian person, you could convert t derivatives into r derivatives. But okay, we work with u and v, right? So just, you don't have to know the exact formula, just by how it scales tells you how that converts, right? Is that okay?
This negative to the top of the beat in the second last line. Over.
Here?
Yeah. Yeah.
Sorry.
Thank you.
Sorry. Yeah. All right. And so the upshot of this and so the upshot in this, again, very sort of silly situation to be addressing with this kind of manipulations, is that our wave equation, du dv, so du dv of psi equals 0, this becomes v over minus u. Right. Okay. And remember, this calculation, all of it only made sense for u negative, because the whole process involves dividing by u at some point with the scale, right? Okay, so this kind of procedure is very important, by which you can reduce just by scaling considerations. You can kind of create, something which was a PDE in u and v. You can make it into an ODE in v, right? And of course, there's something special about v versus u in this. You could similarly convert something into an ODE in u, right? All right, and now I can also, keeping in mind, okay, so I'm going to finish very soon. So keeping in mind this little comment I made here, we can also restrict. We can restrict, right? So this makes sense. Remember, this whole thing only makes sense anyway. It makes sense in u less than 0. But in view of that comment, I can restrict to u equals -1. And then this just becomes, so that v of dv, right, all log u equals -1, this equals 0. Okay, and if I get the solution there, log u equals -1, because of the scaling, I get it in the whole region where this made sense to write it this way. Right? All right, so it's okay. So I guess we'll pick up next time by solving it. We're going to solve this, and like I said, we're going to not restrict to smooth solutions. We're going to allow weak solutions, and we'll solve for it and see what we get. All right, so I guess I'll end there, but I'll take a minute for any questions.
Why did you decide to work with u less than 0 or something? That just for
Eventually, we'll cover u bigger than 0. It's just that you have to why? I mean, some of it is, yeah, it's just we want to cover this whole picture. You have they're kind of these 3 regions. We do these 2, and then later we'll do those 2. Yeah, you could start. I mean, one of them is when we think like physically. I mean, we're interested in things arising in evolution, and so we want to, of course, these are a bit. We'll see that these solutions are a bit strange, but you kind of want to assume that things are nice coming from the past, and so it's sort of reasonable to start here, and make some condition that things are not weird coming in, and then sort of work your way up. It kind of psychologically, it just kind of, you want to go up, but it's all symmetric. You can do whatever you want. Other questions?
So, for like 0 separate so
We will have to do it separately. It's just like it's as if you have 2 coordinate, some manifold that's covered not by a single coordinate system. I mean, it's all like I said, it's all silly in this simple situation, because we could just solve it globally in one go. but it's as if, we have some coordinates that work here, some coordinates that work here. So we solve it first here and then solve, and then with what we know there, solve it in the other one. Other questions? All right, so then I'll see everyone on Wednesday.